This is the Management 565 lecture on simulation. So let me just give you an agenda. So when we talk about simulation, we'll do a general introduction as to what simulation is and what purposes it serves. And then we'll do a simple simulation using the rand function in Excel, coin flips, rolling dice, that kind of thing. And then we'll introduce the if statement, so as a way to make conditionals based on the results of your simulation, which allows you to do things that turn out to be quite complicated done using direct methods. And then we'll move from uniform random deviates that are produced by rand function to random draws from the normal distribution using norm inverse. We'll apply that to simulating project completion times and waiting lines and the stock market. So a simulation is it's an opportunity to use large masses of computing power to simulate random paths through a decision process that is uncertain but prescriptive. So for example, if you think about a stock option, the way stock options are structured is if you have a vanilla call option, you have the right to purchase the stock at a special price at expiration, which may or may not be valuable. So if you have the opportunity to buy the stock for $80 when it's selling for $60, that's worthless. But if you have the opportunity to buy it for $80 when it's selling for $100, that's worth $20. This is actually a very simple rule, and for any randomly selected stock price, you actually can get a nice conclusive determination of value. So where it gets difficult is when you try to find the value of the stock option at some time previous to expiration, because you have a chance it's going to be worth a lot, you'll have a chance that it's worth nothing. There is a solution to this problem that's listed on the slide. So you need to do it involves putting these two carefully calculated values into the standard cumulative normal distribution and using the present value function and natural logarithms. And so while this is a direct formula, discovering it in the first place was rather difficult, and using it is somewhat time consuming unless you have a calculator to do it automatically, and that's just for this particular case of a European call option. And so we're going to instead, our method would be to simulate random stock paths. So pretend that you bought the option and simulate what would happen with the stock and what you would get with the option, and then simulate another stock price path, and value the option, and do this over and over again until we have a large sample of simulated option payoffs, and then use that to generate a value of the option. So the simulation approach allows you to, without necessarily having a ton of fundamental understanding of the situation at hand, to brute force a way to some kind of estimate. And this is important because when we're thinking about business decision making, no two situations may look alike. And so general purpose methods become pretty important. So for example, I can think about the chance I get a heads on one flip of a coin. So what you would do is flip 1,000 coins and see how many came up heads. And similarly, we could flip 2 coins and see how often we got exactly 1 heads, or 4 coins and see exactly how often we get 2 heads. So this is accomplished in our case using the random function in Excel. So rand generates random numbers between 0 and 1. there's a rand between function that generates integers between two numbers. It updates every time a cell is changed. So if you delete a cell or type in a cell, it's going to recalculate all of the random functions in a sheet. So we're going to use random integers to simulate coin flips in Excel. I'll hop over to our Excel sheet here. Line that up. Okay, so we've got so let's do one coin here. You know what? New sheet. We'll do one coin, the one coin case. So when we do a coin, we're going to use rand between. That's an Excel function. And we get to choose a number. So I'm going to do 1 and 2. So I want a random number, an integer between 1 and 2. So 1 is heads and 2 is tails. So I'm going to fill this down and flip 1,000 coins. 1,000, let's see, 1,000, oh, 1,002 coins apparently. So we'll delete these. Okay, and I'm going to take the average. Okay, so we have an average of 1.4875. So that means that roughly 49% of the time we get heads and 51% of the time we get tails. And as I push delete, it's refreshing and we're getting lots of different answers. So you can see there is actually quite a bit of dispersion, and that 1,000 data points is not enough. So if we go all the way down to, say, 4,000, we'll get slightly improved accuracy on our answers. Oh. So that was the wrong one. Let's see, page down. Here we go. I'm going to fill this down to the bottom. Down. There we go. Now I've got our coin flips. Take that average. There. So now we're getting something closer to 50. So we get a little more data, but it still bounces around. But that's the probability we get 1 heads. So now we're going to do the 2 coin case. So I'm going to do 2 coins here, fill those down, and now we want the average of all of this. Wait, let's see. Let's take the sum here of these. Right. So 4 would mean 2 tails, 2 would mean 0 tails, and so on. And then we'll take the average of that. We're getting 3, so that means we have a 50% chance of heads and a 50% chance of tails. Or sorry, a 50% chance of getting 1 heads out of 2 coins, and a 50% chance of getting 0 or 2 heads out of 2 coins. And so next was the 4 coin case. So I'm going to copy this, paste and paste. And then we need to add these. And then double click, send it to the bottom. And average. We get 6. So the average is 6. which that's an average of 1.5 each. But rather than taking the average, we really want to calculate whether we have exactly 6. Right, so if that is equal to 6, right? Because if it's 6, that means we have 2 heads and tails. If we don't have it, then we don't. So value of true, 0 if it's false. And then we'll click that down, and then we take the average of this guy. Okay. So see here that even though we're averaging a sort of 6, the probability that we get exactly 2 heads and 2 tails is something like 30.37%. And that's because we can get a score of 6 with 3 heads and 1 tail canceling out with 1 heads and 3 tails. Now this wasn't true for the 2 coin case or the 1 coin case. So to some degree it's a somewhat counterintuitive result that if you get 2 coins out of 4, it's not 50%, it's something less. But that actually makes sense if you take it to large numbers. So what's the chance I get exactly 200 heads out of 400 flips? It's not actually a very high probability. Okay? So we can find, but we simulated that probability by flipping the 4 coins, right? So here's coin, this is coin 1, coin 2, coin 3, and coin 4. And then we got the sum of those coins, and then here we did an if statement that kicks out a 1 if their condition is what we're looking for, and a 0 if it's not. So these kind of if conditions are very common in simulations because you're often checking whether something occurs. So did we stock out of product? Were there extra people in line at the end of the hour? That sort of thing. So if we have differing behavior that branches depending on the outcome of a random process, it will often mean using an if cell. So the format is you put a conditional in if a cell is less than some number, if the integer, so here's this even or if odd, if a is 1 that's heads tails. So we can use if to filter a lot of things. Okay, so I have a, you try it. So this is out of 4 flips was the probability that 2 are heads. So try to get that 0.375-ish number that I got using your own simulation, and then maybe extend it to the case of 3 heads out of 6 flips and see what you get. So see if you can get my same numbers and then try to extend it for 3 flips, 3 heads out of 6 flips, and we'll pick up when you come back with normal deviation.